Okay. Hello, everyone. Hope you're having a great day so far. My name is Kimmy. I am part of the executive team here at University of Calgary's Information Security Club, and I welcome you to today's speaker series event. Really quick before we get started, we have our attendance sheet for you. I'm going to post that into the comments as well. Perfect. This is super important for you to fill out this sheet, as it allows us to keep track of who is attending our events, as well as give you, the guys, the opportunity to vote in our annual general meeting at the end of the year. So just take a second, fill that out really quickly, and we will get straight into the speaker series event. Okay, I'm assuming that most of you have taken the time out to fill out that quick form. Thank you very much in advance. Okay, so for today's speaker series, we are joined by our special guest, Dr. David William King. I would like to note that Dr. Williams King studied computer science at the University of Calgary and graduated with honors in 2012. Furthermore, in 2014, he earned his master's degree in computer science, and in 2020, he earned his PhD in binary security. Impressive, right? Now, Dr. Williams King has been the Chief Technology Officer at Alpha Secure for the past 3 years. If you have any questions, feel free to type them in the comment section below. We will be answering questions periodically during the presentation, as well as our Q&A session at the end, so stick around for that. All right, without further ado, please welcome Dr. David Williams King.
Hey there, can you guys hear me now? Ping me if you can't hear me, but otherwise, nice to meet you guys. I'm David, or Dr. Williams King, I suppose, these days. And yeah, I'm going to talk about compilers in general, or rather compiling, linking, and loading on Linux systems. So yeah, we'll just go through an introduction, and then there'll be 3 parts here. And after each part, I'll pause for questions. I'm also going to switch back and forth to a terminal a fair amount through this talk. So my hope is that you'll at least, watch what I'm doing and try to follow along a little bit. And please do, ask any questions that come up, whether they're like, can you explain a bit more about this, or what does that technical command mean, or anything really. Yeah, so let's just dive a bit into the introduction there. As Kimie mentioned, I did go to the University of Calgary for my undergrad. But before that, I want to mention something a little strange, which is I grew up outside Calgary in a house that was completely off the grid. So that means it's not connected to the electricity grid. It was using solar panels. It was using windmills for electricity. It was heated by wood. We always had to chop wood and carry it in the winter. Yeah, it's a very difficult environment to grow up in, to be a developer or a programmer, right? Because there was limited electricity to run laptops or computers. But I really think it actually encouraged me to be a hacker because, everything was a challenge. Just like, jury rigging everything up like a solar panel on the roof of the car while we're camping, so that like I can, uh, get some programming done on the computer or whatever. And yeah, so it's a very interesting background, and happy to chat more about it. But I think that like trying to solve those types of problems from a young age really helped me out. After the University of Calgary, I went to UBC, and then I did do my PhD in binary security. And just for maximal confusion, I went to the University of British Columbia as well as Columbia University. One is in Vancouver and one is in New York, in case you're wondering. Yeah, I'm currently the CTO at Alpha Secure, and you can look us up. We basically we try to merge cybersecurity insurance along with cybersecurity technology that we create for small businesses. So small businesses get our tech along with our insurance. So if they do get hacked, then they'll be able to make an insurance claim, just to provide them with better assurances. One other note here is I'm actually a frequent user of coding by voice, which is you might be able to see I'm wearing some gloves here. My hands get very sore if I do a lot of typing these days. It's a medical condition, so I actually kind of made and utilize a system where I can speak, and then voice recognition will turn it into characters and code. That's an entirely separate topic. I've done talks on that before as well, but I just mention it because you'll probably see me use it when I'm using the terminal to talk to you guys about compilers stuff. So when I say voice recognition and you hear me saying things that don't really sound like English, that's what that is. Yeah, so that is me in a nutshell. Off the grid, lots of schooling, and now coding by voice. So I've broken this down into 3 parts. The first part is just the compiling and linking process, which you guys have probably seen in various courses. This is for C. C++ is very similar. As I mentioned, I'm going to be focusing on Linux for this presentation. And often when you compile something, you would just invoke a compiler like GCC or Clang, and you just say like compile.c -o hello. But there's actually at least 2 big steps going on there, right? The compiler that produces .o files, and then the linker that combines lots of .o files together. And although you may not think of it as a step, there's a 3rd step when you go to run a program, and that step is called the loader. This slide is called basic compilation because the rabbit hole goes much, much deeper. So let's start out with that a little bit. My goal with this slide is to basically show you all the different steps that a C compiler has to go through. And most other languages are similar, that are like compiled languages, I mean, like C++, for example. So I'm not sure if you've seen the C preprocessor before, but I'm just going to switch to the terminal here. And if you guys can't see the terminal, please also let us know. But starting from a C program, the first thing that you have to do when you're compiling it is actually run the preprocessor, which is going to handle these lines like the hash include, right? So I'm going to use the voice recognition here. Golf Charlie Charlie space minus sky every space word hello point Charlie tunnel word less enter. So that's my day. I'm always speaking at my computer, whether I'm talking to a person or whether I'm just trying to get some code done. But anyway, this is the preprocessed version of the code. So down at the bottom here was my original, and the rest of this is just a copy paste of stdio.h. the standard input-output stuff. And I mean, it's a bunch of nonsense. What it actually is it's a bunch of forward declarations. So for example, if I'm trying to call printf, then printf is actually mentioned. Its prototype is actually mentioned by doing that copy pasting. And that's obviously the primary purpose of doing a hash include, of doing the preprocessor, is you want to be able to call functions that you didn't write, but that are actually in another library. But anyway, that is actually the very first step of preprocessing. I'm actually going to go a little bit faster through the rest of these, and then circle back a little bit. But after you have finished the preprocessing, then you hit the compiler, like the main part of the compiler, and the job of this is basically to take the preprocessed stuff and produce assembly out of it. And the assembler is a separate entity, again, that is going to take assembly code and produce .o file. So if you looked at the previous slide, the preprocessor, compiler, and assembler together are kind of considered the compiler, if you want to look at it that way. And then finally, at the end here, we still have the linker and the loader as separate steps. So I'm just going to go through each of these in a little more detail, and then hopefully by the end, you will have learned something. So I kind of jumped into this a little bit prematurely here, but the preprocessor, like I said, it just copy pastes entire files. That's kind of slow, and some compilers do things a little differently. Like the Microsoft compiler was the first to introduce precompiled headers, where they kind of preprocess each .h file so they don't have to copy paste the entire thing. And a more modern implementation of that is modules, which I think were first introduced by Clang. And now they're part of the C++ standard. But the preprocessor, oops, and I should have paused my Slack before this. I'm sorry, you guys. The preprocessor is still the kind of the standard to be used almost everywhere. And fun fact, if you're doing a distributed compile where you have lots of computers that are together going to work to compile your code for you, it almost always works by pre-processing the files first and then sending them to be compiled, because a pre-processed file is standalone. That's all you need. You don't have to look at other files on the disk, and you can just compile it and then send the .o file back to whoever requested it. So yeah, you saw a little example of the preprocessor. It's just copy pasting and you get huge files as a result. The compiler is the brains of this, right? It has a front end to actually parse the source code, like your int main and your variable declarations and all that. Front end to parse the source code into an intermediate representation, which is basically a way of representing the program kind of like with data structures rather than with source code. And the compiler will typically take that intermediate representation and optimize it, which is a simple operation that starts with IR and produces other IR, which is supposed to be equivalent but faster. The LLVM IR, which is the Clang compiler's IR, is actually very popular for researchers and people doing optimizations. So in the literature, you will see a lot about LLVM IR. Some compilers, including GCC, actually have multiple levels of IR, like a higher level one and then lower level ones and so on. I think GCC actually has 3 levels of IR. And then finally, the back end is going to take that IR and it's going to generate assembly code as a result there. I'm actually going to try to pause this Slack here if you give me a moment. I do apologize. There we go. All right. Just turning the screen share back on again. Can you guys see my screen? Oh, maybe it has to be dragged back in. Ah, there we go. Thank you. Apologies for the interruption there. So yeah, I was just talking about IR and how there are sometimes multiple levels. The back end is the final step. It takes the IR and then generates assembly code. So you just kind of got those three types of representation: source code, intermediate representation, and assembly code. And you've got, kind of, I should have drawn a state machine, but anyway, you've got the front end to do the first parse. Optimization just generates more IR, and then the back end to generate the assembly code. So a lot of research goes into especially optimizations, right, in order to make the code work well. And the compiler is very CPU intensive because it's basically running all kinds of graph algorithms and like Dijkstra's and crazy stuff to take your IR and make faster IR that's equivalent. So yeah, that's the main compiler. And then finally you have the assembler. And the assembler is basically going to take text representation that looks a little bit like this, either this line or this line. And it's going to turn each of those lines into one machine code instruction. So if you look back at the way that compilers are structured here, let's suppose you're trying to write compiler for a lot of different languages and a compiler that targets a lot of different machines. So if you're trying to target like C and C++ and Fortran and Pascal and whatever, then you can actually just write separate front ends to parse those different source languages and then produce, for example, LLVM IR from all those front ends. Now your optimizations are going to work no matter what the source language. And then finally, you can write a ton of different backends for x86, for ARM, for RISC-V, for MIPS, and whatever other architectures you can think of. And that's basically what LLVM is, or rather what the Clang compiler is. It's a much newer compiler than GCC and many others as well. Like it's newer than Microsoft's compiler and whatnot too. So it has a very clean internal architecture that lets it do this. They actually do have a front end that parses a lot of different languages and backends that generate a lot of different, they generate assembly code, and then they rely on the assembler after that to target the actual machine code. But by splitting the compiler up into these like front end and back end and IR, you're able to get a really powerful tool. And yeah, you guys, if you've done any reversing challenges or whatever, you would definitely have been familiar with assembly and maybe some tools that let you look at assembly. Object dump is one that I'll show in a minute. Pardon me. There are other like reverse engineering tools out there as well that are more powerful. And then finally here we have the linker that is going to take the output of the assembler, which is object files. And it's going to take those object files and combine them together. That's how you produce executables, basically, as well as other things like shared libraries. So LD is the name of the standard linker. GNU, it's part of the GNU project, so GNU LD. You'll also sometimes see Gold. It's another implementation of a linker that Google made. Fun fact, Google was writing Chromium in C++, right? Google Chrome. And they decided to statically link it, which means they take all of the libraries that Chrome depends on and they were throwing them all into the Chrome executable just to make it, able to run on different architectures. And LD, the original one, was crashing because this was such a massive program that it couldn't handle it. It's more than 600 megabytes for like a statically linked Chrome executable if you have the debugging information. So they actually wrote an entirely new linker to handle Chrome and also to be much faster at like much larger projects. So anyway, if you're writing a really big project, you might care about Gold, but otherwise most people just use the original. And the LD, the linker, is normally invoked just from the compiler directly because the linker deals with a lot of system level details and it's quite complicated to actually invoke directly. But we can give it a try. Let's see what happens. So I also have like a hello world program here and I want to go through all the steps so that we can see what they all look like. So let's get started with voice recognition. Command Vim, word hello, point Charlie, enter. Vim quit. Minus Oscar space, word hello, point India, enter. Up to scratch, India, enter. So again, this is just the preprocessed output file, copy pasting. Vim quit. Golf Charlie Charlie space. Minus Sky Sierra space. Word hello point India space minus Oscar space. Word hello point Sierra. Enter. Up to scratch Sierra, enter. So we took the preprocessed code and we ran the compiler on it that had like the front end and then the intermediate representations and then the back end. And that produced assembly code. And that's what this is. Kind of hard to read if you have not looked at it for a long time, but each of these lines that are this color here basically are individual instructions, and they turn into one machine code instruction. This is the name of the function main, and most of the things that start with a dot are they're called like pseudo ops. They don't actually turn into an instruction directly. They just tell the assembler to treat things differently. For example, this line here is saying, you know what, the symbol main is actually global and it's of type function. But these don't actually generate code directly. They just generate metadata. But yeah, so this is assembly. Unoptimized assembly, I might add, because I didn't pass -O to tell it to optimize. And then if I wanted to assemble this, I could now start actually invoking things like AS instead of GCC if I want to. So that would produce the object file for me. It's a little hard to look at an object file directly, but you can use a tool for that. Voice recognition, object dump, word hello point Oscar, tunnel word less, enter. So this object dump here is taking the object file and disassembling it. It's turning it back into essentially the assembly instructions, because assembly is so low level that there's a one-to-one correspondence basically with machine code, right? So these machine code instructions over here turn into exactly one assembly code instruction, and that, you can do that forwards and backwards if you want, because it's a one-to-one mapping. So that's what object dump is doing there for us. It's showing us the code that's actually present inside that object file. And then finally, the last stage would be to link everything together. As I said, it's kind of hard to invoke the linker directly, so let's not start like that. That produced a final executable, and then we can try running it. You can actually object dump executables as well, anything with binary code in it. So you'll be able to see, a bunch of stuff added by the compiler, as well as the original main function that we wrote. Yeah, so okay, I said that we might try invoking the linker directly. Let me see if I can do it. I don't think so, because when you are telling LD to link something, you have to provide all the libraries, the C library, and you also have to provide all of the compiler specific scaffolding that that gives these other functions. So I used to know how to do it, but I don't remember. So you could look it up, or you can ask GCC actually to print the LD invocation that it's using. But yeah, although you can run the assembler directly, I would recommend not trying to do that. So GCC actually forks and runs a lot of processes as it's executing. So it will spawn off, for example, CPP, which is the CP processor, and then it will spawn off AS to do assembly, and then it will spawn off LD to do linking. So if you're ever like doing a really expensive compilation, and you're sitting in top, for example, and watching all the processes that get spawned, then you'll see that GCC actually starts quite a few different things. Did I miss anything? Did we not look at any of these things? There's more to see about executables, but we'll get there when we get there. And yeah, I think I will stop there for the moment. Let me see if I want to say anything else from these slides. There's just one thing I want to say at the bottom there. You see -WL-Q. That is a very strange option that you can use to pass stuff through to the linker. So WL means, hey, GCC, I want you to pass this option -Q to the linker. So if we look at the LD man page, -Q says emit relocations, leave relocation sections in fully linked executables. So that will make the executable a little bit larger, and it has a little bit more metadata. Kind of not very useful, but this is kind of how you get around not being able to invoke the linker directly. You can just pass arguments through to it like this. This is something that I used in my research, the extra relocations. So that's how come I happen to know it exists. Yeah, I think I will go on to the next slide for now, but I will pause shortly. If anyone has questions, please do just type them, and I'd be happy to go into things in a bit more detail. You notice that object dump worked on both .o files as well as executables. There's a reason for that, which is that .o files, executables, shared libraries are all the same file format. They're actually ELF format. That's ELF is the Linux executable format, essentially. It's used by a few BSD operating systems as well, and Mac OS among them. Windows, of course, uses a different file format. And the ELF file format is kind of interesting because you can tell by the name, it says executable and linkable format. So that means you can run it and you can link it. Or in other words, it's designed for linkers and it's designed for loaders, which is loaders are what actually runs a program. So there's actually dual views on the same content here, what the compiler and what the linker care about, and then what the loader cares about. And those are quite different. What the compiler and linker care about are sections that can be merged together. So for example, the compiler will produce like a code section from 3 different .o files, right? Every .o file will have its own code section, and the linker will just assemble them together. It will go, oh, let me put the code from object file A, and then the code from object file B, and so on. And it will make one larger code section. So that's what the linker is trying to do. It's trying to merge stuff together. But what the loader cares about is what actually has to get loaded into memory and at what addresses. So if you look at an ELF file, it actually looks a little bit like this, where different parts of it are split up into sections. And these are the bytes that represent the actual contents. So like the code, the strings, the data. And then those same bytes will be, kind of visible according to a different indexing scheme. So again, this is the same offset inside the file. This is the same offset inside the file. It just so happens that the first half of this segment is actually one section if you look at it from the linker's perspective. But when you look at it from the loader's perspective, it's just going to do one memory map to pull in this entire segment. So it doesn't really care that, that the linker thinks they're different sections. Might be a little hard to get your head around, but basically that's what an ELF file is. It's designed to be an early stage part of the compilation process, right? A .o file, and then it's designed to also exist as an executable. So you have to support like merging ELF files together, and then it's also designed to run efficiently. So it's a very compact and efficient format in terms of what the loader is trying to do. So yeah, it's quite an interesting format, and there's quite a lot of complexity that comes up as well because you have 2 ways of looking at everything. So on the left there we see sections, and on the right we see segments. So this is just a slightly more concrete example. So a compiler will typically generate code, and it will put that in a section called .text. It will also generate global data, that's .data, read-only data, that's usually only used for strings in modern compilers, and then BSS sometimes, zero initialized globals. Anytime you just have a global variable, you just say int x, that's zero initialized. And the ELF format is a little bit efficient in terms of representing those. It just it actually says that the section has 0 bytes for that index, but the segment has 8 bytes for that index. So essentially, you don't take up any space in the file to store those 0 bytes, but then when you load it, you end up allocating space for those 0 bytes. Anyways, so there's sections on the left, and then on the right, these are the permissions in terms of read, write, and execute that you would expect these things to have. So for code, you expect that to be at least executable, also readable on x86 architectures. It's a requirement. Execute implies read, and you also, for example, you want global variables to be readable and writable. You want the 0 initialized global variables to also be readable and writable. And then for read-only data, I guess you probably want read and nothing else. It's actually marked read and execute on x86 because that means you can get away with only 2 segments, right? One for the code/RO data and one for the data/BSS. Again, the loader is trying to be as efficient as possible. So, having a small number of segments, having not very much work for the loader to do will just mean that every time you run a program, that process is faster. So I can show you that a little bit with some tools. I mean, you've probably seen the strings tool before, but there's a couple others that are interesting as well to looking at ELF files. So let's have a quick look at that. Word strings space word hello, enter. So strings is going to go through and just find anything that looks like a string, anything that's a sort of sequence of ASCII bytes. So it's a useful way to find embedded secrets or flags or whatever inside a binary. And there will be a lot fewer strings if the executable has been stripped. Yeah, this one doesn't really have much to start with, so it doesn't matter. Let me regenerate it. The other thing that's useful is readelf. Readelf, word hello, tunnel, word less. I usually use it with these flags. W says I have a wide terminal. A says show me all sections. And readelf is going to show you everything that it can possibly parse out of an ELF file, including these are the sections that the compiler produced. Here's the text, for example, the code. Here are the global variables. And it will also show you the segments. Here they are. So this particular one actually is not optimized because it has 4 load segments, and there's readable, read, execute, read, write. So this shows you the work that the loader has to do in order to bring this program into memory and start running it. And yeah, the section to segment mapping will show you which ones get sorted into which buckets. You can spend a lot of time looking at what's going on here. I think the only other thing I'll mention is the symbol table, which shows you the names of the functions that would have been present. So main should be in here somewhere. Here it is. This shows the address of the function main. That's actually very handy if you are trying to find, like, you just get a crash at a random address or something, and then you want to see, hey, what function was that inside? So there's a program also called nm, which just prints symbol addresses. So if all you want are the symbols, you don't have to use the full readelf. You can just use nm. So yeah, nm is a pretty handy little tool. What else is there? LDD. I'll talk about LDD in a bit when we talk about shared libraries. Anything else? Other important components, the string table, whatever, the symbol tables, yes. What else should we do? I guess I'll just show LDD because that's an easy enough thing to show as well. LDD just prints out the shared libraries that something depends on. So in this case, we depend on the C library, libc, and we depend on the loader. This is the loader. If you look at a more complicated program, there will be a lot of stuff in that list. Firefox is actually a well, let's pick something else then. How about, there we go. This is a PDF viewer. As you can see, lots and lots and lots of shared libraries that it depends on. And so the LDD program is very useful for seeing, what other code does some library depend on. There's lots of tricks you can play with it, which we'll probably go through in a bit. Anything else about ELF files? I don't think so. So let's just try to revisit the compilation stages one last time here. You've got the preprocessor, which just does copy pasting, and it's kind of what handles header files for you. It just copy pastes them into a single file. Then finally, you have the compiler, which is going to do its front end parsing, lots of IR optimizations, assuming you pass -02 for optimize, and then it's going to have a backend that generates assembly code for your architecture, whether that's x86 or ARM and so on. And then finally, your assembler is going to take that assembly code and turn each one of those into one machine code instruction. And this output file will be encoded as an ELF file. So this is where you start getting ELF files. Then the linker is going to combine as many .o files as you want together, as well as other libraries and so on. Those are all ELF files, the inputs, and the output is also an ELF file. And then finally, a loader is what is actually used when you run a program. We haven't seen any evidence of that yet, except when I did LDD here, we saw that the loader was specified at the bottom as a dependency. If you're wondering what this is the kind of like a virtual interface with the Linux kernel. It's used to accelerate system calls. So every program on Linux will have this one here. It's added by the kernel. Almost every program will have libc, and every dynamically linked program will also have a loader in place. So I think that's my first break for questions before we dive even more into what loaders do essentially. So perhaps I will pause here and give you guys a moment to see if you have any questions.
Well, wait a second.
Did you have any questions for me, Kimia, while we're waiting for other people?
No, I'm just trying to get into the whole understanding of it all when you're going next into the next part.
Oh, okay.
You have 3 parts, right? So the first part was just the compiler.
That's right.
And then what's the second and third parts?
The second part is talking about the loader, basically, which is probably not the most complicated exactly, but the hardest one to find information on, right? Because it fits between like architecture and programming languages and operating systems, and no one really studies loaders. So I wanted to spend more time on that than the others. And then the final third part, it's much smaller. It just has some stuff about security and other miscellaneous things about programs, binaries.
Okay, I think we should move forward with the presentation because I'm not getting any comments showing up.
All right. Well, that usually means that either everyone is bored or everyone is over their head. I don't know. I'll try to slow down in case it's the over the head thing. But yeah, let's dive into the next section here about loaders. So
we actually have one question before you start your presentation.
Yeah, sure.
So someone asked, how does distributed compilation work? Is it only beneficial with larger code bases containing multiple linked files?
That's a good question. So the way it works is, yeah, you have a lot of files that you want to compile, and you have at your disposal many different computers. So you want to, what you do is you install the distcc compiler on all of them. For example, there are other distributed compilers. And then when you go to compile your program, instead of using GCC, you just use distcc. And if it's configured appropriately so that it can talk over the network to these other machines, then it will actually send them the work to do. And again, the compiler is the CPU intensive bit, so it will send the compiler work to the other machines. You do the preprocessing yourself on your machine, and then when they send the .o files back to you, you also do the linking yourself, typically. Is it useful only for larger code bases? I mean, it depends what you're working on. I've set up distcc a few times when I was working with things like the Qt source code or just like really big things, for sure. But actually, a good example of it is Google's tool, Blaze. Blaze. Yeah, the internal code name is Bazel, but I think the external name is Blaze. So Blaze is like it's a distributed compiler, and at Google they have all their stuff in one big mono repo. And every time you compile something, it will invoke Blaze, and it will send the code out to like 30,000 machines or whatever it needs, compile it all up, and then send it back to you. And that way they don't have to. No one has to really wait, right? All the machines are able to cache recently compiled files, and whenever someone changes something that actually affects a lot of stuff, you just end up using more machines to compile it. So yeah, if you have the resources and you're doing a lot of native development with C or C++ or similar languages, then it makes a lot of sense to set up.
Awesome.
All right. Thanks for the question. Let's just go a little bit into loaders then. So what a loader does is it copies an executable from the disk into memory, into RAM. So it's basically when you are launching a process from a program, you need the loader to do that. And if you think about what you know about processes, they typically get their own address space, right? Like from 0 all the way to FFF, whatever. That entire virtual address space is meant to be used by a single process. I mean, you first have to allocate the memory. You have to tell the operating system that this is memory that I want to use. Otherwise, you get seg faults. But in principle, all of those addresses are available to one process. And the loader is what makes that happen. So originally, if you looked at this address space, every program would always start at the same address. So like 40,000 as an example. But these days, you'll actually see the base address being randomized through something like ASLR. So I don't know if you've seen that, but if you write a program that just prints addresses, every time you run the program, it will end up with different addresses. Actually, I can show that really quickly here. / papa scratch 3 / papa Romeo Oscar char / word self / word map tab. So this is a feature of Linux that lets you look at any process on the system. Those are all the processes that are there by process ID. And proc self is like your own process. So from cat's perspective, that is cat looking at itself and cat printing out its memory maps. And this was all brought into existence by the loader. And these are the addresses that were chosen for those various components. So if we look at cat, the executable, read, nothing, execute, this is its code. It's the only thing from cat that has the execute permissions. So anyway, all cat code addresses are going to be in here. But if you keep running this, you get different numbers every time. And that's a security feature, actually. It's designed to make it harder for a hacker to actually guess addresses and take control of the program. There are ways to disable it. The easiest way is just to use a debugger. For example, like this. Whenever you're using the debugger, it is going to pick a specific base address of 555, as you can see, every time we run it. And that's just to make debugging easier. You can also use like a set arch command or something to disable randomization per terminal if you want, or system wide. But anyway, that's sort of why addresses often look very random. It's because the upper half of it or so probably is completely random. So yeah, every segment of the program is loaded at a random address. The stack and the heap are also starting at random addresses. That means an attacker can't reuse information from one process to attack other processes, which is actually surprisingly easy to do. So ASLR is a really important security feature. But of course, if you are modeling the attacker, for example, by doing a CTF challenge, you may find that ASLR has been disabled to make your life easier. But real-world attackers have to deal with it. In order to actually attack something with ASLR, you normally need to have a read vulnerability as well as a write vulnerability, or another word for these is a memory disclosure vulnerability that lets you read something, and then a memory corruption vulnerability that lets you write something. Because during the read, you first figure out what the base address is, and then during the write, you put some stuff in that includes the base address. Without ASLR, you don't really need the read vulnerability. You just need the write. Yeah, my PhD research is actually kind of like an extension of ASLR. I tried to locate each function at a random address rather than just the segments at random addresses. And then I was also changing the addresses of the functions as the program ran every couple of milliseconds, which is about as hard as it sounds. It's very challenging, and most programs may not like being transformed that way. So you have to be somewhat clever about how you do it. But yeah, it's kind of useful to know what ASLR is, just so that when you are printing addresses, you're not taken by surprise. Yeah, I think that's all I'll say about ASLR. So let's talk next about shared libraries, which so you might have heard of static libraries, which are on Linux, they're like lib something.a, the .a archive files. They're basically a way to bundle a lot of code together into one executable. As I was mentioning, that Google Chrome was doing, they took all their dependencies and they bundled it all together, and they made one thing. That makes it easy for the loader to load, but it's really large. So shared libraries solve one main problem. If you have 100 processes that all use one library, do you really want to load 100 copies of that? So how could you share a library across different address spaces? Imagine you've got like 2 processes running, and they're different processes, so they're going to use their address spaces in different ways, right? So address 1000 might be free in one address space, but address 2000 might be address 1000 might be free in one and taken in another. So it's really hard to figure out like what address something should live at. So on Windows, actually, DLLs have a default address that they try to use, but that is just an optimization. The right answer is that libraries have to be okay living at any address. So what the loader will do is it will try to say, for process A, I'm just going to use address 1000. For process B, I'm just going to use address 2000. And the same code mapped at different addresses has to work correctly. So that's something that the loader is kind of doing behind the scenes there for you. The main artifact of getting this to work properly is that there are actually trampolines so that the executable can call library functions, because the executable doesn't know what address the library is going to live at. So when the exe wants to call printf, first it looks up in a table that says printf is at address 1000, and then it actually calls address 1000. That's called the PLT, or the procedure linkage table, if you've seen that before. But yeah, so if you look at this cat example that I was doing, let me get out of debugger. So for cat is just like our hello program. It just depends on libc and the loader and this funny virtual thing. So when the loader actually loaded cat, it had to load cat itself, libc, and the loader. So these are both considered shared libraries essentially, and they're just like the regular executable. They're subject to ASLR, so every time you run it, they're going to be at different addresses. And the interesting thing is that I actually only have libc, the standard C library, loaded into memory once. It's only going to take one set of physical memory pages. It might be mapped into 10,000 different virtual address spaces at different virtual addresses, but it's actually only taking up the memory, the physical memory in my machine once. So that's why if you look at the virtual memory used by a process, like look at this. This Chrome is using 1,000 gigabytes of memory apparently, and this other Chrome is using 33 gigabytes of memory, and so on. Like, these are insane numbers that don't make any sense. And the reason for that is a ton of this type of sharing going on, right? Like, if you add up the total amount of virtual memory space used, it might look quite high. But if it's stuff like libc, then it's actually only taking the physical memory page once. So shared libraries are actually like really important for modern software. Otherwise, everything would be putting a much larger burden on your system's memory. So yeah, that's kind of what I had to say about shared libraries. Do I want to say anything about this? Not really. It's sort of complicated for libraries to access data in other libraries, or for libraries to access functions in other libraries. And there's like these two entities that are used to track that. One is the global offset table to track data, and one is the procedure linkage table to track function calls. And if you're really curious, you can look at an object dump of an executable and see what is in each of those two things. I have a couple of slides labeled gory details, which I will probably skip, just FYI. So loading basics, we've already said loading means copying an executable from disk into memory. Where this actually starts is with the kernel, the operating system kernel, the Linux kernel. It has a simple loader built in that is capable of loading static executables only. So it can't handle shared libraries. For everything else, the system loader, which is called ld.so, is invoked. And yes, this is a super confusing name, right? Because the linker is called ld, and the loader is called ld.so. Yeah. Traditionally, I think linkers and loaders are really closely related, but that doesn't excuse picking the exact same name for each. But anyways, so the kernel, if you're using ld.so, first the kernel will load ld.so, which is a static executable. And then that loader, ld.so, will recursively load all the other shared libraries. And then finally, that loader will actually just jump to the main function, into main. So if you look at the cat example one last time, that's why the loader ended up mapped into memory here. Because what happened is the kernel comes along and it creates the stack, the VDSO, that weird virtual interface, and then it loads LD, which it's able to do because it's a static executable. Then LD goes and says, oh, I should load cat because that's the program that is actually being run. And then it does so. And then it goes, wait, what are the shared libraries that cat needs? it basically runs this, right? And then it goes, oh, libc is something that cat needs, so let me go and load that. And again, it's probably already mapped into some other processes, so it will just reuse the virtual memory mappings and not waste any space. Yeah, that's all I think for that slide. Do we care about gory details? I'll just mention one gory detail, which is kind of fun. Most operating systems, Linux included, will have something called copy on write pages. So let's say you fork and you had one program and you fork and now you have two programs, right? Initially, those programs will share all the same physical memory pages. Remember, I'm talking about physical memory versus virtual memory, right? The new process will get its entirely new virtual address space, but all the pages will be the same physical pages because they're all the same and it doesn't really need to represent them twice. The pages will all be marked copy on write, which means if either process writes to it, then that process will get its own private copy. Only at the point when a write comes in does the Linux kernel bother to make a copy of that memory page. So yeah, if you take an operating systems course or whatever and you learn about paging and so on, you can look into copy on write. That's how a lot of this stuff is implemented. So let's skip over the rest of that. And I'm going to skip this for now too, I think, unless someone has a question about memory models. So yeah, finally about the loader, we already saw LDD to be able to see like what the loader is going to load. To see which library symbols come from, LD debug equals all. Okay, let's try it. LD debug equals all. So this is me just setting an environment variable. So I could go like export LD debug equals all. This is like special bash syntax that only sets the environment variable during the execution of this one command. So it won't be set for my future executions. So I just ran that. It prints a bunch of stuff about what it's trying to look up and so on. I guess I'm actually curious about the hello or the puts symbol. So here we go. Transferring control to int main in there. Then it's puts is called. It looks and says, hey, is puts inside hello? No. Okay. Let's check the next one. Is it inside libc? Yes. Okay. And so on. So you can actually see like what the loader is doing. Every function call that was not inside the original library or the original executable, it actually looks up and does a search and then binds it and then writes down the addresses and does all kinds of stuff. So yeah, the loader is doing a lot of stuff behind the scenes there for you. This LD preload actually lets you override. You can put this earlier in the list. Let's say this libmyprintf has a function called printf. You can put this earlier in the list with LD preload than libc. So even though a regular program is calling printf, you can say, actually, I want you to call myprintf instead, and you can do extra stuff. It's called like library introspection, or I forget the exact term for it, but it's kind of a convenient way because you're doing a lookup on every shared library function call anyway. So you can do the lookups as the original program intended, or you can kind of hijack them and do your own stuff for debugging purposes or whatever. Using like LD library path and so on is actually a really convenient way to take one Linux executable, even if it has shared libraries that it needs. You can copy all those shared libraries, bundle them all up, and send it to a different Linux system and run it. As long as the kernels are compatible, and almost all kernels are, it will actually let you run a Linux executable somewhere else. So there are a couple of projects actually that do that for you, that would like bundle stuff up and they're like, run Linux anywhere or whatever. But that's all they're doing. They're just copying the shared libraries into one place, and then they set the environment variable LD library path to the current directory, and the loader just looks there for the executables or for the shared libraries instead of on the system. Um, yeah, I've got one slide on how to debug things. Okay, if you get a compiler error, always look at the first error and turn on warnings, because here's what happens. People write bad code, and then compiler writers write warnings that detect the bad code. But if they just like enable those warnings, then the people who wrote the bad code get annoyed because they're like, my code used to compile, but now I get 10 million warnings. So all the useful warnings are all hidden behind flags like this, but those are the flags that basically turn on everything. So highly recommended for both C and C++, and any GCC or Clang compatible compilers. For the linker, if you're getting messages about invalid relocations, try compiling position independent with those arguments there. And if you're getting missing symbol errors, you can actually run nm, which I think we went through earlier. You can run nm on all of your existing .o files to see if the symbol is present in any of those. So yeah, these compiler and linker debugging steps here are basically all I ever do whenever there are errors at the compiler or linker stage, and it lets you really investigate pretty much any issue that could arise. And finally, there with the loader, if you're getting missing libraries, like you tried /hello and it says can't find libc, you can actually just use LDD again, look for libraries that are not found, find them somewhere online, like you can download old Debian or Ubuntu shared libraries from their respective sources, and then just go LD library path equals like that. So I actually have, let me see if I remember where I put it, but I have a really, really old project that I compiled during my undergrad at the University of Calgary. I took a games programming class, and this was the game that we made. And I don't even know when it was compiled exactly. I guess it would have been 2012. So it's 11 years old now. And I copied all the shared libraries into this directory here. And if we say LD library path equals dot, we can check to see whether the executable can find all of its dependencies, and it can. There's nothing that's marked. There's nothing that's marked as not found. And as you can see, it's actually finding the libraries in / here. If we looked at the LDD from something else, most of the libraries, or let's look at the Ocular one as an example. Most of the libraries are on my main system, right? They're in user lib somewhere. But by using this loader hack, sorry, that's hard to read. By using this loader hack, I'm basically able to say, you know what? Just use the libraries here instead. And there you go. It's a fun little game. And yeah, that's only possible because the Linux kernel is still supports the same system calls that it did in 2012, and all the shared libraries are copied here, present here, and then we hack the loader to tell it just look here instead. Basically, sort of treating this executable as if it was statically linked, right? If it had been statically linked and it had all these libraries embedded in it, I would probably also still be able to run it. But I would probably annoy anyone on their system that was wondering why I was using a lot of memory. So this is like the best of both worlds, right? You're able to compile it so that it uses shared libraries and uses the memory well. And you're also able to bundle those shared libraries up and ship them with the executable in case someone else wants to run it. So yeah, this is kind of my top tricks for debugging compilers, linkers, and loaders. And you can get really far with any kind of errors or any kind of older systems or anything like that by trying those out. Yeah, so this is my end of my second part. Let's see how we're doing for time. All right. If you guys have any questions, please feel free to type them in. I'll give you a minute. I will rely on Kimie to tell me if there are any questions.
I don't see any right now, but I was a little curious on that game coding class you took.
Mhm.
I saw the name Hex Racer game.
Yes.
Could you just give me like a short rundown of like what it does exactly? Just curious.
Yeah, for sure. Um,
Like, was it just for you practice to? Oh, wow.
yeah, it's you can do multiplayer, and also um, actually let me run it properly so we can have a look. There's a server and a client, so I'll just run the server there. I have to run the server from the command line because if the program itself tries to run it, it doesn't provide the LD library path, so it doesn't work. But yeah, you can kind of create as many AIs and so on as you like, hop into a game. It's playing
Wow.
sound to me. I'm not sure if you're able to hear it. The
I
point of the
cannot,
game is to
unfortunately.
paint your team's color like this, or erase opponent team's colors. And I'll whoops, trying to do too many things at once. I'll get a speed up bonus if I'm on my own color, and a slow down, like a penalty, if I'm on an opponent team's color. Um,
Oh, I see. That's so cool.
yeah, and you can check out how the AIs are working. There you go.
Did you have a hard time debugging this the first time you were
Yeah, I mean,
trying
it's
to
in C++.
execute?
There are all kinds of crashes and memory errors. Oh no.
So it works great 11 years later.
Yeah, it works. It works pretty well.
Okay, so really quickly back to the presentation, we do have one question.
Yeah.
If we had changed LD library path to current directory, are we still be able to use other shared library not in the current directory?
Yes, this is basically specifying a place to look first, and then it will go look in normal places. So if you look at the man page for ld.so, you can look up the library path. Let's see what they say about it. Here it is. A list of directories to search for elf things. And by default, it looks in the system places after that. So yeah, it can be really handy. For example, if you want to override just one thing, you could do so, right? So let's say, I don't know, let's copy ocular into here. Let's try to override only one of the things that ocular uses. So here, it's using libresolve. So let's pretend we got this libresolve from the internet somewhere, and we want to use it instead. We basically do this /ocular, and we check the LDD. And there we go. We're able to use our /resolve, but everything else is just using the system stuff. Yeah, so good question. And it's kind of like an include dir for GCC, right? Include some directory here. It puts that at the beginning of your search path, but the standard locations are still in your search path, or the path environment variable, come to think of it. That's a good question.
We have a comment actually.
Hmm?
Someone would love to hear about the PLT plus GOT control flow process if there's time.
All right, sounds good. I think I have a gory details slide about that. So we can go into that. But yeah, I'll go through the third part here, and then circle back on that.
Awesome.
All right. Well, let's dive a little bit into the third part, and with a gory details added to it. The basic executable security. So these are things that most of the time the compiler and the linker and the loader are going to do for you, just to defeat some easy attacks. So the first is like making the stack non-executable. You used to be able to just inject code on the stack and run it. It's kind of silly. Position independent code so that you can get ASLR. Protecting the global offset table, which is the one of the things we're going to talk about in a minute, by making it read-only so that attackers can't override it and point it at their own locations. This is something that the loader will do after it is done loading, because basically the loader has to write to this, but nothing else is really supposed to. So by default, the loader's a little lazy, and it will just leave this writable. But if you ask it, the loader nicely, it will leave it writable while it's writing, and then it will go back later and mark it as non-writable. You will probably want to enable the built-in heap protections. GCC has some like libc type heap protections, and Clang has a really powerful one called address sanitizer. If you're getting a little more sophisticated, I think control flow integrity is like making sure that jumps in the assembly code are going where they're supposed to. It used to be a research only type of thing, but it actually got added to hardware. Intel introduced some hardware instructions to support it, and then in no time at all, it somehow ended up in the compilers and then in every single Ubuntu executable. It happened during my PhD in like less than a year. The CPU started supporting it, and then it was in Ubuntu. It was amazing. And then there's a fun paper called Eternal War in Memory, which is basically what this is, because attackers and defenders always trying to one up each other. And I stole an image from that paper in case you're wanting to see something really crazy, but this is like all the different things that an attacker might try to do. And at the bottom there, different types of successful attacks. So you can see all kinds of different defenses in here: memory safety, code integrity, blah, 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 executable randomization. So, and these ones as well. So anyway, as you can see, there's a whole like research area, of course, and the war in memory has a lot of participants. The problem is that most of these defenses are actually pretty expensive. So the ones on this list here are basically free. Some of them are only free once hardware support was added, like control flow integrity. But that's often the way security works, right? No one wants to use it unless the cost is free, and often that needs hardware support. So anyways, I think we talked about the Google Chrome instance already when you're trying to make a static executable. So moving on, other essential tools. Make is very, very useful whenever you're compiling things. Highly recommend you learn it. And GDB, very handy. The debugger or other debuggers, very handy as well. In that same games class that you saw my game from, there was one classmate that I had when asked, what's your most difficult programming challenge? And, some of us were like, my design isn't good, or like, I always have to Google things or whatever. This person said, my worst programming challenge is segmentation faults. And I was like, you can run GDB and then it will tell you the line at which the segmentation fault is occurring. And his mind was blown. He was like, you know how much time I've wasted on this? Because, anyways, it's, I think it's a very good use of time to learn a little bit about a debugger. And it's not really a lot, like even just learning how to run, and if it was to crash, BT for backtrace. That's it. And that will tell you like the exact function trace callback that caused the crash. So that's what I mean by GDB. Version control, tmux. If you haven't tried one of the things on this list, pick one and spend a weekend or something. They're all going to accelerate your development quite a lot. So that's, I think, it, except I did promise to go back into the gory details of, not that one, shared libraries. So let's talk about it really briefly, and then we can call it quits. So okay, so this goes a bit into the memory model, which I also skipped because it had gory details. But basically, code inside a shared library doesn't know the address at which it's going to get loaded, which means that when it wants to access even something else in its own code, it has to use what's called a RIP relative reference, which is basically RIP is the instruction pointer, right, in x86, which means that you always say like 100 bytes further ahead than me right now, or 100 bytes further back than me right now, at a higher or lower address. So let's look at a quick example of that. Object dump, word hello, tunnel, word less, enter. Slash Mike Arch Indian Noi, enter. So here's main. So let's say so the call instruction, for example, is actually a RIP relative instruction. So if you look at the encoding of the call instruction, hex E8 just means call, and then this is a slightly small negative number. If you look at the encoding, it's like, I don't know, negative 300 or something. You could put it in a calculator and find out if we wanted. This is the least significant bit here, the least significant byte. I'm sorry. So this is actually going backwards to address 1030 right here. And the difference between 1030 and this address is what is encoded in here. So that's the first thing to know about shared libraries, is they have to use code that is independent of whatever address it lives at. And position independent executables are actually the same way. So on 32-bit machines, RIP relative referencing used to be really expensive. You had to dedicate a register and say this register is going to store the current base address or something. So you went from 8 registers to 7 or whatever, and it was quite expensive. But then when they moved from 32-bit x86 to 64-bit x86, they actually added this RIP relative referencing. Actually, I should just have pointed at this. Here's another example, right? This is adding a constant to the current instruction pointer. So here, this on the right-hand side, the object dump has done the calculation for us of what the current instruction pointer plus EC4 is, why it's 2004 in hex. But anyway, so 64-bit x86 kind of added this ability, and therefore it became cheap. You didn't need to dedicate a register anymore. And therefore, everyone started using position-independent code, and it made libraries cheaper as well. So that was a big win. Again, making the hardware do it for you. Basically, add more hardware features so that the security and cool security and cool compiler things were more accessible to everyone. So let's see how main is trying to access puts, which is basically, if you don't know, puts is just printf if you're just printing something with a new line. It just writes S and then automatically writes a new line. So since we said hello world \n with printf, the optimizer turned that into puts. So anyways, main is trying to call puts here. How does it do it? Well, first it calls an address 1030, which is actually labeled the puts at PLT. Okay, so here's puts at PLT. It's a little bit of code. This is actually called a trampoline. And what the trampoline does is it does some indirect jump here. And then, after that, there's a push 0 and another jump to PLT. So what is this nonsense? Well, this is actually, as we can see, 4018. Can't see it in here. What should I look at? I should look at... I want to see the global offset table. I should look at readelf, I guess. Readelf. Word hello, tunnel, word less, enter. So here's the global offset table. it is quite small. This is the size of the table, hex 28. So that's like, I guess, 5 8-byte values, because this table is just an array of addresses. And the the array of addresses is basically the actual location of puts once it has been looked up. So when you first call puts, the address that's stored in the global offset table is actually the address of the very next instruction. So when you first call this, you jump to here, and it goes, okay, I'm just going to follow this jump, and it follows it, and it's like, okay, that was basically a no-op. And then we push an identifier, an index 0, and then we jump to a special location, which is then code provided by the linker. It actually goes up to here, right? And then this like says which library we're in, and then jumps to the sorry, not the linker, jumps to the loader. So what happens the very first time you call puts is it basically says, hey, I want to look for function number 0 in library number whatever, library number 0. And then the loader comes along and says, oh, okay, what's function number 0? Okay, it's called puts. And then it does a search for puts, as we saw earlier. And when it's done, it puts the address of puts back into this location. And the whole reason for that rigmarole is next time you call puts, you already know the address, so you just want to jump straight to it. So second time you call puts, you'll jump to the PLT entry, and then this will jump straight to the real address of puts. That's kind of why it's called a trampoline, right? Because you jump to here, and then you jump to the real address. So why did they do all this craziness? Because we don't know the distance between wherever we're calling puts from. We don't know the distance between this address and the real address of puts. To make matters worse, it might even be further than 2 gigabytes away. And the call instruction can only go plus minus 2 gigabytes because of how large it is. So for both those reasons, you need to have this trampoline. And is there anything else? Yeah, there's actually one other thing, which is when we did the LD debug equals all, we were able to see this lookup of puts, right? So this environment variable, when it's present, the loader will see that, and it will just print a bunch of stuff whenever it's doing things, right? So this is the loader saying, all right, I'm done loading things. Please, I'm just jumping to main now. And the next time the loader knows is when main has decided to call back into the loader to request the function puts. So the loader is still like present during the execution of the program, right? And there's actually this function called dlopen, which lets you load shared libraries at runtime. And dlopen is basically just another call into the loader, right? You're basically saying, hey, I'm just main, I've been running for a while, and now I want to load my plugin.so. And that's just another call to the loader. So the loader's code is alive and well, and used for many things. And the other fun thing about this is being able to bind. LD bind now equals 1. So if we go LD bind now equals 1, along with LD debug equals all, what we see here is there is no puts lookup. And why is that? Because this is saying bind immediately. As soon as you load a shared library or the executable, look up every single one of its shared library calls and take their addresses and put them in that global offset table so that they're all pre-resolved. This means it takes quite a long time to load, but it means that, the loader is not really invoked later on, which means performance is going to be more stable. It means if you're in the debugger, it's fewer steps. There's nothing worse than being in the debugger and trying to single step through stuff and you end up in loader code. So this is extremely handy when you're doing debugging, and sometimes when you're doing like performance profiling and stuff like that, you want every run to be the same performance. So did I miss anything? I did miss something. Technically, the global offset table is also used for global variables. So I lied earlier because there's two global offset tables. There's this one and there's this one. This is the global offset table used for the PLT. So that contains the addresses of functions. And if you wanted to see the addresses of global variables, you would see, for example, error is a global variable that's located in libc. So if we look at the object dump of that code, now that we're accessing error, you'll see a, what is this, 4034. That's inside the global offset table, I imagine. And first we actually load, let me optimize this. It'll be a little easier to read. Yeah, here we go. So we're calling printf. We need to load the address of our string, like the hello world string. And then we also need to load the address of error. And this address is located inside the global offset table, I believe. Let's have a quick look if we can actually spot it. 4034. This is readelf output again. So 4030 is right here. 4034 is inside the BSS. So I guess error is a bad example. Because it's located inside the executable, it looks like, which means that the code I was looking for that accesses the global offset table would be inside libc rather than inside our program. But anyway, you can kind of take my word for it. It's also a level of indirection. First, you load the address of the global offset table. Then you go to, like, index number 3, and then you load that address, and that tells you the real address of the global variable. And that's how one shared library can access another shared library's global variable. Because there's only supposed to be one global variable ever, right? Which means it has to exist in one place, and everyone else needs their true address of that global variable. So hopefully that's more than enough gory details for all you folks. But yeah, if you want to learn more about these types of things, object dump, readelf are your friends. You can find a lot of information online about elf files. There's one page called the teeny tiny elf, something like that, where someone tried to make the tiniest elf possible, which is great fun. So you could read that or other stuff. There's really no shortage of things online. Yeah, if you have any other questions about this, you could always reach out to me. It's very related to my area of PhD research, right? So it's all in my head at this point. Yeah, I think that is all that I have prepared for today. So thank you very much, and let me know if there are any final questions.
I was muted this whole time. Oh my goodness. I said thank you so much for your wonderful presentation. It was truly educational. And I also agree with the comment that my brain hurts from so much information being absorbed.
Yeah, it was a lot for one pass, but hopefully you found some interesting things that you didn't know beforehand, and that's the main goal.
It was really fun. I did have one question for you though, and I wasn't sure if you mentioned it in the very beginning.
Mm-hmm.
I apologize if it's already been mentioned, but what inspired you to pursue a career in binary security? Like, was there some sort of underlying passion, or like everyone was doing it that was around you, so you did it as well?
Yeah, I actually took a class at the University of Calgary. Yeah, I didn't mention that, did I? I took a class at the University of Calgary, which was John Aycock's viruses class. At the time, he was offering them viruses and malware class. And it was a really great experience. Like, you have to learn about ELF files so that you can write your own ELF virus. And then you have to write an antivirus that can clean up all your other classmates' viruses. And it had to treat the lab as sort of high security. Every time you log in, you get a completely blank virtual machine. I was trying to use version control, but the only version control on the system was CVS, which is probably so old you've probably never heard of it, but it's like the grandfather of Git. And CVS refused to run as root. So every time when I booted on my system, I had to go into the CVS executable, go to byte offset like 2000 or something, and replace one of the bytes with a no-op, because that was the address at which it was checking if you were root. And I would do that, and then I could check out my code, and then I could actually proceed. And the way I figured that out was I just wrote a GDB script to essentially go through every single instruction. It was very slow. I let the computer run for an hour or two, came back later, and then it printed the exact instruction before it exited, basically. And I was like, okay, that's the instruction that I need to know up. And then that let me use version control. That's how interested I was in using version control, even on viruses assignments. But yeah, it was really fantastic, and kind of got me interested in that area. I think it's something that is not very well covered by most classes, right? Is this, like I said, this kind of the space between compilers and architecture and operating systems, right? You just kind of go, oh, it probably all works together. But there's a lot of scope for security in that area. And and then in my master's program, I started trying to make code that could randomize itself. And it took me all of my master's and then most of my PhD to get that actually working. Because I was trying to make
though.
Yeah, it does work. It does work, but it was very had to kind of learn all those different pieces myself, because there really are not very many good resources for it, right? Often the answer is just go read the loader code, which is not the easiest code to read, let me say. So yeah, that's where it all started for me.
That's amazing. One class sparked your whole journey.
Mm-hmm.
It's beautiful. Thank you. I did notice a few questions in the chat, if you're willing to stay for that.
Yeah.
One person said, so you said that the trampoline jump can jump only as far as 2 gigabytes. If for some reason we need to jump further, would we have more than one trampoline?
Good question. The the jump where you encode how far you're going can only go 2 gigabytes. A jump where it's dereferencing a pointer. So let me show you quickly here. This type of jump can only go 2 gigabytes because the offset is written into the instruction. But this jump is literally saying, read 8 bytes of memory from this address, and the address itself has to be within 2 gigabytes, but read 8 bytes from that address and then jump directly to that location. So if you're using this type of jump, like an indirect jump, then you can encode whatever address you want in there, and you'll be able to jump all the way to your target destination in one jump. But there are many other cases where you actually need trampolines to trampolines when you're looking at binary security. So you might think that's too crazy, but it actually does happen quite a lot. It's a good question.
I have a headache. I'm looking through. It's just a bunch of good comments about how they want malware classes and what a great experience you had. Unfortunately, we won't be able to experience what you had. So at least we have you to live vicariously through.
Yes, indeed. It was a very interesting class, but there's a lot of materials online as well. And like I said, a lot of it is just sort of in this like loaders type area, right? Like how do executables actually work? And then the viruses class itself would also have covered, how you actually attack that. How do you inject yourself as a literal virus, which means a program that infects other executables. It's all very interesting stuff. Actually, for the final assignment, we were trying to write an antivirus, and we were all very proud of our antiviruses at that point because they could catch every virus that our classmates had written, right? Um, and uh, and then the instructor came along, and he would just come to your computer, and he would just type a command. He's like, "Oh, I'll just scan this," and you're like, "Okay," and you point your virus scanner at this executable that he was indicating, and it would crash every time, and everyone's like, "What happened?" And then he didn't tell us, right? But then at the end, when he'd gone around to everyone's computers and verified that like every single person was crashing on this executable, he said, "Oh yeah, before this assignment started, I installed a rootkit on all the machines. So if you try to access that, I trap it from inside the kernel." And we're like, "Of course you did." So it's a very interesting class for sure.
Wow, amazing. Uh, Thank you again for your amazing presentation, and thank you for your time coming on our speaker series event this evening.
Yeah. Thank you very much for having me. I think some of you guys know me on Discord. You guys can always reach out to me there. My handle is Serious Elf. You can find me in the Magpie, um, the Magpie CTF, for example, or you can be old school and email me. I think I put my email at the top. If you want to reach out, I'm always happy to talk about this. It's like I said, it's kind of hard to find information on, but it's really critical to security in general. And yeah, always happy to chat.
All right. If there's no more further questions, thank you everyone who came out tonight. Thank you once again for coming for our event. Have a good night.